In this video, we're going to be identifying zero force members during the analysis of a pitched roof truss. In this example, we're going to identify the zero force members in a pitched roof truss and then use them to understand the main load path through the structure. Before doing any detailed calculations, there are two useful rules of thumb. First rule applies at an unloaded joint with only two non-collinear members. For that joint to remain in equilibrium, both members must carry zero forces. The second rule applies to an unloaded joint with three members, where two of these members are collinear. In that case, the third non-collinear member must be a zero force member. Let's apply these rules to the truss. We'll start at the peak joint K. There's no external load acting at the joint, and only two non-collinear members meet there, GK and IK. To see why both members must carry zero forces, assume initially that they carry an axial force, with theta measured from the horizontal. The horizontal component of each member force is a proportion to cosine theta, while the vertical component is proportional to sine theta. Applying horizontal equilibrium, the horizontal components must cancel. This tells us that the forces in GK and IK must have equal magnitude. Now consider the vertical equilibrium. The vertical components of the two assumed member forces act in the same sense at the joint, so for their sum to equal zero, the two member forces would need to have equal magnitude but opposite sign. So horizontal equilibrium tells us that the forces must be equal, while vertical equilibrium tells them they must be equal and opposite. The only values that satisfy both conditions are zero. Therefore, GK and IK are zero force members under the idealized loading shown. There's an important modelling point here. Although this is drawn as a pitched roof truss, the zero force result at the peak depends entirely on the loading condition. In a real roof, loads from self-weight, roofing, snow, wind or purlins would typically be transferred into the upper joints, including the ridge. If an external load were applied at joint K, the peak members would generally become active and would no longer be zero force members. So a zero force member is not permanently a zero force member. Its force depends on the particular loading condition being analysed. Next, let's look at joints B, H and D. Each of these is an unloaded joint with three connected members, where two of the members are collinear. Starting with joint B. The two bottom chord members lie in the same horizontal line, so neither of them can provide a vertical force component. The only member capable of producing a vertical force at the joint is BG. But there is no external vertical load acting at B. Therefore, from vertical equilibrium, the force in BG must be zero. The same reasoning applies at joint H. The top two chord members are collinear, so their forces act along the same horizontal line. The only non-collinear member is CH. Since there's no external load acting at H, vertical equilibrium requires the force in CH to be zero. And finally, at joint D, the two bottom chord members are again collinear. The only member capable of providing a vertical force component is DI. With no external load acting at the joint, equilibrium requires the force in DI to be zero. So without carrying out a full truss analysis, we have already identified 5 zero force members: GK, IK, BG, CH and DI. This is one of the main advantages of identifying zero force members before solving a truss. They allow us to simplify the structure and make the active load path become easier to understand. Now consider what remains after these members are removed from the force analysis. The 15 kN load is applied at joint C, and it's transferred through the active members and eventually into the supports. The bottom chord forms part of the tensile load path. These members are being pulled, so they're in tension. The two internal diagonal members connected to joint C are also in tension. The inclined outer members, however, are being pushed and therefore act in compression.